So, what we're going to do in our lab activity today is we're going to support the concept of chemical equilibrium that you're getting in the classroom. And we're going to do it through lab measurements so you can kind of put a different approach to understanding these concepts. So we've chosen an equilibrium that's represented here on the board. And it allows us to observe one of the chemical species by absorbance because it's colored compound in water. And the other species are colorless. So we're going to control the amount of iron 3 ion and thiocyanate ion that we put in a mixture. And that's going to form this colored compound, the iron thiocyanate complex. And that is how we're going to measure the amount of this new product that's formed. And so we have to talk about using Beer's law to determine that amount of that concentration. We're going to use Beer's law to do that. And let's take a look at this equilibrium. So it's a fairly simple equilibrium involving two reactants and a product. And when we write this equilibrium in this way, we are going to be able to write an equilibrium constant for this expression. By writing it this way, we've established a forward reaction, and then we write the double arrows there to represent that it can go backwards and forwards and come to some equilibrium, dynamic equilibrium. So the equilibrium constant is expressed on this page, but I'm going to rewrite it so that it's the way you saw it in class. We're going to have products over reactants, and the concentration of a product, iron thiocyanate concentration, is in the numerator, and then in the denominator we have both reactants, iron 3 ion and the thiocyanate ion. And because the stoichiometric coefficients are all 1 in our equilibrium, then these concentrations are all to the power of 1, and it makes it for a simpler expression for the equilibrium constant. So we are going to be able to determine these three concentrations and be able to calculate an equilibrium constant. So what we're going to do to start off is we're going to do one solution where we put a lot of the iron 3 ion in solution and a much smaller amount of thiocyanate. And under those circumstances, all of the thiocyanate is going to be bound up in this complex, iron thiocyanate, which is colored, and we'll be able to measure that amount of absorbance. That, with Beer's law, is going to allow us to determine an equilibrium, molar absorptivity. For later solutions, we're not going to overwhelm it with the iron 3 plus ion. We're going to put more equal amounts of these, and then we can see how much of this complex is formed and use those concentrations to determine its equilibrium constant. Let me scroll down on the page a little bit here, if you follow along, and we can look at some of the solutions that we're going to deal with in this lab. So we have one iron 3 complex, iron 3 ion. It's with the nitrate ion, so it's completely dissolved and dissociated in solution. And that's at the highest of these three concentrations. It's 4 times more concentrated than this second iron 3 solution, and it's 80 times more concentrated than the thiocyanate solution. It also has a spectator ion of potassium. So nitrate and potassium are spectator ions in this equation. So you can easily see if we make mixtures of its most concentrated solution with the thiocyanate, that it is going to have an excess of the iron 3 plus. The latter solutions will be made up of combinations of the last two of these. Now, if you'll go with me to the second page, Part A is preparing. Okay, here we are on the second page of our lab guide, and I'm going to go to part B, which talks about Beer's law. And I'm going to zoom in on this equation here. This tells us how absorbance is related to concentration. And this quantity epsilon here is the molar absorptivity. And L is the path length through this cuvette, and that is normally 1 centimeter. So knowing these two constants, epsilon and the 1 centimeter path length of the cell, allows us to directly relate absorbance to concentration. So for part A, we're going to actually have an idea of knowing the concentration of our complex, our iron thiocyanate complex, and we're going to calculate epsilon. So that looks like, if I move this over and make myself a little space, what we're going to do for part B is solve for epsilon. So epsilon is equal to absorbance divided by L divided by the concentration of our complex. And we're going to measure that in the lab. We're going to know that L is 1 centimeter, and we're going to know what the concentration of our complex is and be able to calculate epsilon. Now let me talk for a moment about units of this. It's not explained well in the lab guide. Absorbance is unitless. And so the units of epsilon are 1 over centimeters times molarity. So inverse centimeters, inverse molarity are the units of epsilon. When we get to the next part of the lab, you're going to be measuring an absorbance, and you want to use that to find the concentration. In that case, we need to use this value for epsilon from this part B, and we will carry that forward. So if I make a little more space here, in that case, we're going to want to find the concentration from the absorbance divided by the epsilon value, molar absorptivity, times the path length. And when we measure absorbance, we know this value from part B. We can calculate the amount in concentration of the iron thiocyanate complex. So we'll be using Beer's law